Good afternoon and welcome to the Liftoff webinar. My name is Christine Longroy. Thank you for joining us today. I'd like to introduce our panelist for our Liftoff webinar. Again, my name is Christine Longroy. I'm the Senior Director of Ecosystem here at Lyft. Welcome and thank you for joining us. Today we have Stephan from InfraTec Infrared presenting the easy way to deploy 1 million temperature sensors. During today's webinar, I just want to remind everybody to include your questions and answers in the question and answer section during the presentation. We'll be taking those at the end. Again, I'd like to thank you for joining us.
Welcome to Liftoff Webinars, brought to you by LIFT, the National Advanced Material Manufacturing Innovation Institute, where we drive American manufacturing into the future through technology and talent development. LIFT is a public-private partnership where we convene and connect government, industry, and academia in the fields of advanced materials, manufacturing processes, systems engineering to enhance America's manufacturing competitiveness, national economy, and national security.
Hello, I'm Stephan Larmann. I'm with InfraTec in the US, and InfraTec is a manufacturer of calibrated infrared cameras. And if you're working with joining or additive manufacturing operations, then temperature is probably one of the parameters that you need to measure very often. And I would like to show you today how you can do that with the help of calibrated infrared cameras. I will use linear friction welding as an example to show you the possibilities, and I will show you first the setup we used. We used a linear friction welding machine. If you've been to the Lyft facility, you will have seen it. The way that works is you have those two pieces of metal, steel coupons in this case, that get rubbed and pressed against each other until they heat up so much that you can actually forge them together. It's an easy way. It's a very good way to join metals. We used 3 cameras total. This here is one of the infrared cameras, and then we had what I call a normal camera working in the visible spectrum, so just like the human eye or RGB camera, and we had a second infrared camera to record the data, and so that you get an idea of what the process actually looks like. This is a short video that I took with my cell phone to show you how that welding process works. So when we say calibrated infrared, there's 2 parts. The infrared part is the one that I would like to explain first, and we distinguish infrared, most of you will know this anyway, from the visible spectrum. So one is a cell phone as an example for a camera that records images in the visible spectrum, and an infrared camera works in the infrared spectrum. The visible spectrum is typically somewhere between 380 nanometers and 750 nanometers, and the infrared spectrum continues on the red side. That's why it's called infrared, and goes from the just under 1 micrometer up to 15-20 micrometers. That's the range that is typically used for infrared cameras. And the key fact that is applied for these cameras is that every piece of matter, every object, emits radiation in that infrared part of the spectrum purely based on its temperature. So there's a direct correlation between the infrared radiation emitted from a piece of metal, in this case, and its temperature. So you can easily use that, of course, to measure temperature. So let's zoom in a little so we can see it a little better, and then I will, as I said, move forward in the scroll bar until we start seeing what I would like to show you. and that should be around now. Let me zoom in a little with the infrared. And go a little further up, and there we go. There's that white line, which indicates that there's a heat generated by the friction, and we can see that clearly in the infrared image. We don't see anything yet other than the movement in the visible spectrum camera. So let's move a little further down, and you can see the heat. There's more and more heat generated up to the point that we now have, which is the metal starts glowing. So there's now so much heat has been generated that the metal starts glowing, at least at those 2 points, and that coincides nicely with what we see in the infrared image. Just have to zoom it a little, magnify it so that the dimensions match a little better. Okay. And I would like to take this part now to explain what's called the Planck curve and how that fits in the basics of this entire way of measuring temperature. So this is the Planck curve, and what do we have here? On this axis we see the wavelength of the radiation that we're looking at. In this case we have the visible spectrum here. It's a very small range, it looks like. It's, as I said, 380 to 750 nanometers, and then continues into the infrared. Goes up to from 1 micrometer to 20 micrometer. On this axis here we have a measurement for the intensity of radiation. You can look at it as energy or power, and the curves are for a specific temperature each. So the way you would read this is, let's look at this one here, the 300 degrees Celsius curve. That's roughly 570 Fahrenheit. So that means a body, in this case it would be a standardized black body, that is at 300 degrees Celsius temperature, would radiate this amount of energy at 16 micrometers, this amount at 8 micrometers, and so on. So the curve shows the spectral radiation per wavelength. What's interesting about this is that the curve is unique for each temperature. So if you can measure the radiation, you know exactly the temperature, because the curve for 305 degrees would be a little higher. So if you measure the area under the curve, you can use that for pretty accurate measurement of the temperature. And the great thing about this is it is a universal law that is pretty much, law of nature that is pretty much independent of what you're looking at. And the other thing that is interesting is you can see at this point here all the curves at these temperatures, a couple of hundred degrees, a couple of hundred Fahrenheit, they all pretty much have no intensity showing in the visible spectrum. Only when you get to something like 700 degrees Celsius, you can see that. You can't really see it well, I apologize for that, but you can guess that this curve kind of scratches on the red part of the visible spectrum. And if you go to higher temperatures, it goes even further into the visible spectrum. So what this means is, if you look at this temperature, that's roughly the temperature at which iron would start to glow dull red, dark red, and this is exactly what you see. So once you reach this temperature, the metal will start glowing. That means it radiates in the visible spectrum. And that's what we see when something starts to glow. If the temperatures get higher, then it will go to a bright red, it will go to orange, and at some point it will go to a white glow. And one other thing is, at very, very high temperatures, you could technically use this part also to measure, to make calibrated measurements, but you wouldn't be able to do anything in this temperature range. So that's for almost everything that you would do on planet Earth. You would typically use an infrared camera. If you go to solar system measurements with very high temperatures, you could use other parts of the spectrum. And let's put that in correlation with our two videos. Okay, let's just take a quick look at how that relates to the videos we saw. So this here is the infrared at the beginning when the temperatures were still low, but visible in the infrared spectrum. So that's the temperature was somewhere around here, where it wouldn't scratch on in the visible spectrum. So there was nothing glowing here in this part. And this part here then is when we reach the temperature maybe 700 degrees Celsius, 1200 degrees Fahrenheit, when it started to glow faintly red. Okay, last slide with the Planck curve, and then we'll go back to other things. So the way cameras, calibrated infrared cameras work is they integrate a part of the spectrum, and typically you would find cameras working in the long wave range of IR, which is somewhere between 7 and 14 micrometers, or in the mid wave between 1.5 to 2.5 and 5.5. So they integrate the area under the curve, and that's how they determine the temperature. So we talked about the infrared, and we also talked about how they're calibrated. And just to finish that, there are non-calibrated cameras widely used. You could see a picture here. So they would typically be used for things like surveillance, night vision, and those can be equipped with sensors that work in the near infrared NIR or shortwave infrared SWIR. And when it comes to calibrated cameras, you would typically be looking at mid-wave or long-wave infrared. At very high temperatures, as we've seen, you can use shortwave infrared also calibrated, but then you're really limited to very high temperatures. Okay. Calibrated infrared cameras, so they offer many advantages: non-invasive, contactless, remote. You get very good spatial resolution, can be down to micrometers if you put a microscope lens on them. They're very temperature change sensitive in the few 10 millikelvin range, very accurate, 1 Kelvin or 1%, depending on the range. And you can also record fairly high frame rates, not quite as high as high-speed cameras in the visible spectrum, but still pretty high. So the infrared camera delivers a spatially distributed temperature measurement. Each pixel is a temperature sensor, and each frame shows you the XY distribution of a temperature. And if you combine that and take many frames in a row, you have also a time resolved signal. So you can compare that to connecting a large number of thermocouples to a data logger and then let it run and work with the data afterwards. And that's one of the I think important points I always try to make is these are always presented as images, but in reality they're actually numbers. So we put the values, we map them to different colors. You can use black and white, gray, or all kinds of color maps, depending on what you want to show. And images are of course a lot easier for us humans to look at than just numbers, but it is actually both. So each pixel is a number, numerical value for a temperature measurement, but typically you would see those displayed as images. Okay, and I think that's pretty much all I wanted to say about those basic things. I'll just go through, just show you a couple of nice images, short video clips of other applications that may be interesting to see. All right, here we have wire arc additive manufacturing. It's a little video clip, and we see a photo on the right that shows what it would look like in the visible spectrum. Okay, and let's go to the next one. This is a bunch of videos, some of them run parallel, showing laser powder bed fusion additive manufacturing applications. So they're always very colorful, always very nice to look at. Another area that is where cameras are used a lot is in testing, mostly non-destructive testing, but sometimes also for destructive testing. This year is, for example, stress test, where specimen periodically stressed, and you can use special techniques. In this case, it's a technique called lock-in thermography to find the hotspots, which would then point out whether there's any weakness, any anomalies in your material. Another thing they're used for is to check welds to see if they're consistent, if they have any voids or faults inside. One common method is to flash them. So most thermographic methods are based on the principle that somehow you change the temperature, you get some energy in there, and then you see how it's heating up or how it's cooling down. So in this case, for example, the weld was, you could see that here in the previous video, the weld was flashed from behind and imaged from the front. And then in the thermographic analysis, you could see this part here gets hotter. So the heat conduction is better. Presumably the weld is better here, and this part stays colder. So probably the connection is not as good, which means there may be some voids. The weld is not as consistent. And this is a little video showing an automation system. So these are two robots. Each of them has a camera and a flash, and you will see a flash here in a second. There it was. So it would flash the weld, and then the other camera would see how it's heating up and cooling down, and then look at any anomalies that would point to any voids or anything that is not correct. Okay. All right. This is the end of my presentation. If you're here doing the live broadcast, then still be here for some questions, or if you watch this at any point later in time, here's my contact information. Feel free to reach out. Okay, thank you very much.
Thank you, Stephan. Great presentation today. So we do have some questions. Are you ready to get started?
Yes. Thank you, Christine.
Excellent. So since we're all on planet Earth, and it was really helpful for you to kind of describe the importance of this calibrated infrared camera and all of its technical capabilities. Obviously, very high temperatures, really important, the non-invasiveness. I particularly liked how the image is really numbers and not a picture. So from a non-technical person, I appreciate that. We all know how important like checking welds are. So thank you for a really great presentation. So I'm going to kick us off. And could you describe like what in-house expertise is needed to use this thermography?
Well, I would say everybody with a technical background, like from a lab technician to some engineering background, would not take a long time to understand all the intricacies of a system like that and use it, to generate valid data. Not very difficult. There's a couple of things you need to know, but that's what we're here for also, to support that.
Of course. There's a few additive questions here. So was the IR camera placed inside the build chamber in the laser powder bed fusion?
It doesn't, generally speaking, the camera just needs to be able to see what it's supposed to record, what it's supposed to look at. It can be, it depends a little bit on the setup. Oftentimes there's not a lot of space inside, and it may have to go outside. It depends a little bit on the camera. It can go from small, like fist size, up to maybe shoebox size. It really depends on the camera, but as long as the camera can, and you can use different lenses, so you can go further away and still get the same resolution. But the cameras, of course, they're electronics, they're optics, so it can't get too hot. You have to make sure they're within the environmental specifications. So anything like electronics.
Excellent. We have another question. It's similar. How would cameras be mounted in a, laser powder bed fusion AM setup? You sort of described it, but is there anything else you want to expand on that question?
Yeah, laser powder bed fusion is a little different. Additive manufacturing can be very different things with plastic extrusion. Laser powder bed fusion typically works under like a special atmosphere, special gases, inert gases, and so the camera typically with those the cameras can't be inside. And then so you have to look through the outside. They usually have a window that's laser safe, so people don't get accidentally lasered. You may have to put in some kind of special window, one that's transparent for infrared. I've had situations where I went out for tests and it would work with the existing window, but that's not always guaranteed. It can be tricky, but laser powder bed fusion, it would typically be outside, and then really depends. You can have angles that work, and you can have the powder bed can be low, and the window won't really allow you to look at it in a very productive fashion. But they're always made, the windows are always put in so that people can actually see it. So it's usually visible from the outside. I don't know if that answers the question, but laser powder bed fusion camera would be outside most of the time.
Got it. Thank you for that.
Maybe,
go ahead.
Maybe if anybody is really thinking about building a new system, what you could do then is foresee a viewport, for example, on top of it, that would allow you to use a camera on the outside and still have a good view from top. I know that's some of the things we discussed with the systems you have at Lift.
So it looks like another additive question coming in. This is on a part. Could this be used to predict residual stress in an additive part?
You could. I'm not sure I understand the question. The thermography you could use to detect that, to analyze that. I mean, when it says to put that stress into that part, you could use that to analyze it. You would have to use something else, some more mechanical, to put the stress in there. There's also ways you could it's often combined, thermography is sometimes combined with digital image correlation, where you can find out those, analyze those stresses. I'm not the expert on those systems, but we have companies that we work with that do that kind of combination.
That's good to know. Yeah, thanks for sharing that. So another one here, does the high temp heat of a certain high melting point metal do long-term damage to such in-process IR camera? I'm going to say infrared camera. So does that make sense? Do I need to repeat that?
No, I understand the question. Not if to go to very high temperatures, because the radiation increases with the fourth power of the temperature. So there's a very large span, many magnitudes of radiation intensity, but it's not a problem as long as you get a camera that has attenuation filters put in for that temperature range, and then there's no limit, because you just reduce the signal that gets onto the detector. This is true for so-called cooled cameras. There's other types of cameras that are called microbolometers. They work with a different principle. Those would be more prone to develop like ghost images if they're exposed to radiation too high for longer periods of time. But it can be handled, let's put it that way.
Okay, that's good. Can you provide specific examples of how this calibrated infrared camera has improved accuracy? And we've talked a lot about additive, but is there specific industry examples where this technology is currently employed in making a difference? Is it something that you could share today, or would this have to be taken offline?
You mean specific examples like actual user names?
Yes, like where this technology is actually in application in industry.
Well, I know we guys have an NDA with Lyft, but I would imagine in this context, I could say that Lyft uses it for many of the things they do. I mean, you have your own camera and everything, so I don't know exactly where you use it, but you're one of them. Most of the cameras we have in the field, there's usually an NDA involved.
Sure.
We do have some examples for customer names on our homepage, but we're not usually at liberty to give out anything we learned when working with them, installing a system or solving an application. But I'd be happy to talk to anybody, and if anybody is really interested, my contact information was on the last slide. I'd be happy to help anybody. I love that stuff.
Another one, can you provide certain details about calibration process specifically for the high temperature data, since I happen to see that temperature measurement accuracy of plus minus 1K is possible?
Yeah, the cameras are calibrated with the black body at a given temperature. So and those black bodies are then also referenced to standards, by companies like NIST or PTB in Germany, for example. So then we use the black bodies that are certified to calibrate the camera. So all the cameras are calibrated to a temperature, which means that you would typically calibrate the entire system. So if you get a camera with 2 or 3 different lenses, which you may need if you have varying situations, then each lens would have to be calibrated together with the system. So you get a end-to-end calibration certificate.
Excellent. Looks like we have one more question. And you sort of talked about like what factors should be considered when deciding if this is right for a specific industrial application. Is there anything else you'd like to add as a result of that question?
Well, I think if you need the biggest advantage these offer is they're non-invasive, so you're not in touch with your object directly. You don't have to install any thermocouples. So if non-invasive is important, if you can be at a safe distance, if you need spatial distribution, and if you need temporal resolution, this would be an advantage. They're not always, I mean, if you can get away with 10 thermocouples, you probably be better off with the thermocouples. I mean, probably cheaper than buying a calibrated camera. But as soon as you really want to see temperature distribution on a larger surface, or faster measurements, or long-term measurements, or you can't get anything in close enough to your object or put a thermocouple on there, then the camera is, I think, a good choice.
Excellent. One other question that did come in, and maybe it's, does the camera have any application in the medical device industry? And I'd like to have you answer that, but then I'm like, are there other industries that are big adopters of this technology that you could share or expand on?
Yeah, in medical device industries, there is maybe two categories. Many medical devices, as soon as you get close, if they get implanted, or if they get put under the skin or close to somebody's body, then temperature can be a critical factor. So companies that make those, they're always concerned of getting sued for somebody getting hurt with their device. So let's say it's something electronics that needs to be implanted into somebody's body. You want to make sure that it never reach certain temperatures under no circumstances. So they often use that to monitor. This is used more in research, to research the thermal management, thermal capabilities of the devices they're using. And it doesn't sound like medical, but for example, virtual reality systems that you put on your head, they often have LEDs or lasers incorporated. So you have to make sure that nobody gets hurt if they have to wear that directly on their skin. And so that's that aspect. The other aspect is anything that gets used for medical use. Let's say a simple example, you have surgical devices that somehow, they also get used during surgery, of course, and they may be put together in different parts. They could be plastic, for example, and you don't want to use any glue to join these, because you don't, then the glue would technically could end up in somebody's body. So that it may be a lot easier to just use ultrasound welding to match parts, and then that's, of course, the quality of the weld depends on reaching the right temperature, not too low, not too high, and homogeneous across the uniform across the weld. So you could use cameras to monitor that. That could even be done in production in line.
Thank you for sharing. Well, that wraps up all the questions that we had. They were great questions. Thank you to the audience for asking those great questions. Stephan, I appreciate you sharing why the calibrated infrared cameras are important. I appreciate you joining us today. Thank you, everybody, for joining us. I'd like to remind you that November 20th, we will have our next liftoff webinar with EOS, who is going to be presenting on additive minds, turnkey solutions for supplier enablement, strengthening the manufacturing industrial base. So mark your calendars for November 20th. Stephan, thank you. It was a pleasure talking to you today. I appreciate your amazing technology. Have a great day, everybody.
Thank you. Thanks, everybody.
Yeah.
Thanks, Christine.
Bye-bye.
Thank you.
Bye-bye.